Greetings, everybody. Learning as a hobby here. As promised, I want to go over my summary for Chapter 3 in Peter Smith's An Introduction to Formal Logic, second edition. So that's what I'm going to do in this video. I'm also going to do the exercise set, I think, in the video because the section is kind of short. So we'll do both. We'll do the summary, my summary for the chapter, and then we'll do the exercises as well. All right, let me bring up my notes. All right, and like I said, this chapter is kind of short, but there is some interesting stuff in it. I'm really actually looking forward to the next couple of chapters, which deal with proofs, but we have to get through this first. So let's do that. Okay, so in this chapter, we say a little more about the idea of forms of inference and about the schemas we use to deploy them. Sorry, to deploy them. So we said in previous sections, logic, the subject of logic studies the form of arguments or the structure of inference steps, right? And we talked about what a deductively valid argument is, and so on and so on. If you haven't seen those videos, go to the playlist. I'll put the link to it down below in the description bar. There's also, I should mention it because it's been a little while since I made one of these videos. There's a website for the book, which I'll put the link to down below as well. Okay, so section 3.1, more forms of inference. So here we have an argument that we've already looked at, which was labeled argument A. We have two premises. First premise is no Welshman is a great poet. Premise two, Shakespeare is a Welshman. So the conclusion three, Shakespeare is not a great poet. The author says this, along with the Clinton and Bush arguments, which you could see in the previous videos that I made, stated in section 2.3 are deductively valid. So is the following argument, which we label A prime, right? Again, two premises and then a conclusion. Premise one, no 3-year-old understands quantum mechanics. Premise two, Daisy is 3 years old. So conclusion three, Daisy does not understand quantum mechanics. Right. So the inference steps in these arguments are all valid, not because of anything to do with the content or to do with poets or presidents or 3-year-olds, but because of the meaning of no and not and the way that these logical notions distribute in the premises and conclusion. So any inference step of the form, no F is G, N is F, so N is not G is deductively valid. And then I just have a note written here. N stands in for a name, whereas F and G stand in for expressions that sort things into kinds or are used to attribute properties. Right. And then we have a definition here for what we mean by these letters. So we call letters like N, F, G, and G in the above that stand in for various different replacements in a schema, schematic variables. All right, we have another couple arguments here. B has the premises, some philosophy students admire all logicians. Premise two, no philosophy student admires anyone irrational. So three, no logician is irrational. And then we have B prime, some opera fans buy tickets for every new production of Tosca. Premise two, no opera fan buys tickets for any merely frivolous entertainment. So conclusion three, no new production of Tosca is a merely frivolous entertainment. So B and B prime are both deductively valid, and they follow a different um, schema, which we have written here below. Some F are R to every G. No F is R to any H, so no G is H. And any inference step of this type is also valid. Right? He makes a note here about is or are R2. That's kind of confusing to say out loud, but is used to stand in for a form of words expressing a relation between things or people. Okay, so we have now used schemas to display three different types of valid inference, which I have listed here below. I won't repeat them because we've talked about them already. Any argument instantiating one of these patterns will be deductively valid. Right? The way that all, every, and any, some, no, and not distribute between the premises and conclusion means that inferences following these schematic forms are necessarily truth preserving, which, if you remember, is the whole point. That's what we want. Okay, here are three more examples of deductively valid forms of inference. I won't read them out again. Again, you could pause your screen and read them if you like. Um, but we'll move on to section 3.2, four basic points about the use of schemas. So take now the familiar form of inference, all F are G, N is F, so N is G. Does the following argument count as an instance of the schematic pattern? So here's the example. He's calling this argument C. So our premises are all men are mortal, Tweety is a Robin, so the conclusion, Donald Trump is female. And the argument made here does not follow it's not an instance of the schema that we just talked about. But why is that the case? All right, we have the reason here. The whole point of using recurring symbols and schemas representing forms of inference is to indicate patterns of recurrence in the premises and conclusion. Therefore, when we fill in a schema by substituting appropriate expressions for the symbols, we must follow the rule, same symbols, same substitutions. So that's why the above argument is not an instantiation of the schema that we had written above. All right, what about this argument that we have written here called argument D, right? The premises here are all men are mortal, Socrates is a man, therefore Socrates is a man. So does this also count as an instance of the last schema? And the answer, of course, is yes. This time we've been consistent in our substitutions for both occurrences of F and G, even though we substituted in the same way each time. The author says we will allow this, and the reason that we're going to allow it is because it's deductively valid, right? So after all, D cannot have true premises and a false conclusion. In other words, it's deductively valid, so it's truth preserving. Okay, but just a note about an argument like that. Of course, D is not very persuasive. An argument will not persuade you if the truth of its conclusion, of the truth of its conclusion, if you already have to accept it as a premise. Okay, how about this argument here? Socrates is a man, all men are mortal, so 3, Socrates is mortal. Okay, the validity of this inference doesn't depend at all on the order in which the premises are stated, so it is an instantiation of the schema that we looked at. So, the order that you state the premises in makes no difference as to whether they can be true and the conclusion false, or vice versa, whatever. So that would still be an instantiation of the schema that we had talked about. All right, lastly, what is the relation between the symbolic schema presented at the beginning of this section and its three variants below? So they're all the same schema, just with the variables changed out. So they're all sort of saying the same thing, if you want to think about it like that, right? The only difference uh, is in the representation, not in the form of inference that they're specifying, right? It's just a change in the name, not a change in the form, if that makes sense. So remember, what we're trying to reveal is a pattern of recurrence. Don't confuse schemas with forms of inference. These four schemas are just alternative ways of representing the same form or pattern of inference. Okay, section 3.3, arguments can instantiate many patterns. And this is the last section for this chapter. It can be tempting to talk about the form of inference step exemplified by an argument, but we do need to be very careful here. Argument E is trivially an instance of the entirely unreliable form of inference that we have written here, A, B, so C. Right? This is an unreliable schema because, for example, you could have A and B be true, but C be false, right? And remember, we want our arguments to be deductively valid. All right, exposing some structure in the individual propositions, but still ignoring all important recurrences. E also instantiates the equally unreliable form of inference. All F are G, M is H, so N is K. Right, so this is also unreliable. And now filling in enough details about the structure of the inference step to bring out an inferentially reliable pattern of recurrence. E also instantiates, as we said before, all F are G, N is F, so N is G. So you need the recurrences there of the schematic variables. But we could go further. E is also an instance of the perfectly reliable types of inference that we have listed here. Example 4 is all F are G. Socrates is F, so Socrates is G. Um, Example 5, all F are moral. Sorry, it should be mortal, not moral. Let me just fix that. All right, all F are mortal. N is F, so N is mortal. And then example 6, all men are G. Socrates is a man, so Socrates is G. Obviously, these are valid forms of inference. We've just chosen to replace some of the schematic variables with constants, if you want to think of it like that. But the recurrences are preserved, so the truth preservation works, right? The inference is valid. Okay, we could even go to the extreme, take the inference to be the one and only example of the reliable type. All men are mortal. Socrates is a man, so Socrates is mortal. All right, these are all instances of that schema. Oh, sorry, this would only have one instance, right? Itself. There's no such thing as the unique form or pattern of inference that a given argument can be seen as instantiating. That's not to deny that schema 3 has a special place in the story about E. It's the most general but still reliable pattern of inference that the argument exemplifies. Right. And so in other words, this is the one that they're talking about. This is example 3, schema 3. This just gives just enough structure, but no more than we need to see that argument E is valid. Okay, and then last thing, it's common to refer to a universally reliable form or pattern of inference, in other words, one whose instances are all valid, as itself being valid. Okay, and then we get to the exercises. So like I said, if you notice, this was kind of a short chapter, so I'm going to do the exercises at the same time in this video instead of making two separate videos. So let's go through the exercises here. And again, the exercise set here is kind of short as well, so shouldn't take us too long. All right, question A, which of the following patterns of inference are deductively reliable, meaning that all their instances are valid? If you suspect an inference pattern is unreliable, find an instance which has to be invalid because it has true premises and a false conclusion. So I'll just go through these kind of quick. And I should mention also, like I said at the beginning of the video, I'm going to post a link to the book's website down below. And you can see in the author's website all of the solutions to the exercises in the book. So, if you want to try these on your own and check your answer through the author's solutions, you could do that too. So, like I said, that'll be down below if you want to look at that. Okay, but these are my solutions. So, 1, some F are G, no G is H, so some F are not H. Clearly, this is a valid argument, right? There's no way that the premises can be true and the conclusion false. That's again what we mean by a valid argument. He's also saying reliable. It means we would say that it's reliable if it's valid. The inference step I'm talking about, right? Example 2, sorry, question A, part 2. Some F are G, some H are F, so some G are H. This one is not reliable, so I'll give an example of an invalid instantiation of this argument. Some real numbers are rational, some irrational numbers are real numbers, so some rational numbers are irrational. All right. Question A, part 3. All F are G, some F are H, so some H are G. This is also valid. It satisfies it. All instances are valid of um, this inference step. All right. And same thing for uh, part 4. No F is G, some G are H, so some H are not F. Again, all the instantiations of this are valid, so it's a reliable inference form. All right, number 5, no F is G, no H is G, so no H is F. This one is not reliable because there are some instances that are not valid. For example, no irrational number is rational, no transcendental number is rational, so no transcendental number is irrational. Um, if you don't know what obviously I'm choosing examples from math because that's what I know. Um, but if you don't know what irrational numbers are or transcendental numbers, I'll let you look them up. I won't explain it here. All right, and then part six, all F are G, no G is H, so no H is F. That's also a reliable or valid form of inference because, again, all instantiations of that argument are valid, meaning you can't have true conclusions and sorry, true you can't have true premises and a false conclusion. All right, question B is very similar, so maybe I'll just actually go through this kind of quickly. One and two are reliable. Three is not reliable, and I'll explain why. So here, there is an odd number of F, there's an odd number of G, so there's an even number of things which are either F or G, and I gave an instantiation here that is not valid. There's an odd number of integers in the interval from 1 to 5. There's an odd number of integers in the interval from 5 to 9. So there's an even number of integers that are either in the interval 1 to 5 or in the interval from 5 to 9. That's invalid because the conclusion is false, but the premises are true. Right. Part four is also invalid or sorry, unreliable. Um, all F are G, so at least one thing is F and G. And here's my example. All even integers that are odd are real numbers, so at least one integer is both even and odd and a real number. Clearly, that's not valid. All right. Also, five is not valid. Sorry, it's not reliable. He says you refer in that last thing in the box. We said we could talk about inference patterns also as being reliable, as being valid. So hopefully that's not confusing. But M is F, N is F, so there are at least two F. This one is not reliable. Here's an example. John is the only son of Wes. Wes's firstborn is the only son of Wes, so there are at least two only sons of Wes. Clearly, that's invalid. Right, six is valid, so I'll just skip over that. And then question C is kind of interesting because it gives some background. Arguments of the kinds illustrated in A are called categorical syllogisms or just syllogisms. First systematically discussed by Aristotle in his prior Analytics. I hope to get around to studying Aristotle's work at some point in the future. Um, I've made videos about this in the past, so if you're a viewer of the channel, you probably know this, but right now uh I haven't been making videos, but I am working on Plato. Okay, anyway, these syllogisms are formed from three propositions, each being of one of the following four forms, which have traditional labels. So they're labeled A, E, I, or O. So A is all X or Y, E is no X is Y, I is some X or Y, and O is some X are not Y. These medieval labels supposedly come from the vowels of the Latin affirmo, or in other words, I affirm for the proposition, for the two. I didn't word that correctly. For the two propositions, A and I. Oh, sorry, I affirm for the positive two. Sorry, I can't even read my own writing. But apparently that's where the labels came from. And nego, in Latin, represents, I deny. So I deny for the negative two, which is E and O. Um, I don't, I don't know the history of it, so if that's true, I assume that the author, knows where this comes from. So I don't know. But anyway, I thought that was an interesting little tidbit. A syllogism then consists of two premises and a conclusion, each having one of these forms. The two terms in the conclusion occur in separate premises, and then there is a third or middle term completing the pattern, as in our six schematic examples above. Two questions arise. Right. Question one, which valid types of syllogism of this kind have a conclusion of the form A, which is all S are P, use M to stand in for the middle term in a syllogism. There's actually only one type that works, which is the one that I have written here. All S are M, all M are P, so all S are P. Right, and then question two, which have a conclusion of the form O. Some S are not P, and there's a bunch of these. So I have them listed here. I won't read them all out to you, but if you want to download a copy of my solutions, again, they're available on the Patreon page. You just have to become a member, which is $3 a month. Or you can look at the author's solutions, which you can download for free from his website, which again, the link will be down below. All right. And then Part D, ancient Stoic logicians concentrated on a different family of arguments, using A and B to stand in for whole propositions, and not A to stand in for the denial of what A stands in for. They endorsed the following five basic forms of arguments. Indeed, they held them to be so basic as to be indemonstrable. And here are the five forms. If A, then B, A, so B. Form 2, if A, then B, not B, so not A. 3, not A and B, A, so not B, so not B. Number 4, A or B, A, so not B. And 5, A or B, not A, so B. And the author asks the question, which of these principles are acceptable? Which, if any, are questionable? And he wants us to give illustrations to support your verdicts. So here, this is my answer. Again, the author goes into more detail on his website if you want to look at the solutions there. All are reliable except possibly four, which depends on whether or is being used in the inclusive or exclusive sense. In mathematics, we usually use the inclusive or, unless stated otherwise. In natural language, usually or means the exclusive or, meaning one or the other, but not both. The inclusive or means one, the other, or possibly both. So for example, 3 is a real number or pi is a real number. 3 is a real number, so pi is not a real number. So that would be, an example that of argument 4 that doesn't work. What about these further forms of argument which are correct? And here, I don't think, yeah, I just said whether I thought they were or not. So I'll just go through them. 6 and 7 um, are not correct. I guess that would be like not reliable, right? I put a star next to 10. I'll explain that in a second. In my view, 8, 9, and 10 are okay. The reason for the star here is that when I put a star next to my solutions for Smith's book, it's that what that means is that the author actually has something interesting to say in the solution to that problem. So let me see if I can actually bring that up here, and we'll read what he has to say about number 10 here, which is this one, not A, so A. As we will see on a standard or classical conception of negation, this is valid, or at least it is if we, for example, ignore cases of vagueness. Bill is a borderline case. It isn't the case that he is definitely not bald, but he isn't definitely bald either. More about this principle in due course. Um, I study mathematics, so we don't like vagueness. So I don't, if we were going to make an argument in mathematics, we would avoid vagaries if at any cost. So to me, this not A, so A seems like it should be valid in the cases that I would be considering. Um, so that's why I put a star next to that one. Okay, and then he says, what about these general principles? 11 and 12, are okay. So I'll just read out the principles here. If the inference A, if the inference A, so B is valid, and the inference B, so C is valid, then the inference A, so C is valid. That's an important principle for when we make arguments that are comprised of strings of little arguments, right? We want the truth to be preserved throughout. So there's a kind of transitivity here. 12, if the inference A, B, so C is valid, then so is the inference A, not C, so not B. And again, these are, useful ideas when you get to start getting to around to actually making arguments for mathematical proofs and so on. The author here, this book is not focused just on the subject of mathematics. It's generally meant for a philosophically minded audience. So, but we have some other books that we're going through that focus just on mathematics. So anyway, that's the end of this chapter. So I'll end the video here. Like I said, it's kind of a short chapter. How do I stop this? Okay. Um, like I said, I am looking forward to the next few sections because the next section is on proofs. So I'm interested to read what the author has to say about that. Um, and that'll be the next video for Smith. Okay, so I'm going to end the video here. Let me know what you guys think down below, and I'll see you in the next video.